here we go. I have taken two unrelated papers and shoved them together with some birthday wishes. So this is going to be a wild ride. So we're going to start with a basis theory primer in honor of the birthday boy. And we're going to make it real simple. Some of you have seen this slide before because it is my standard slide when talking about frames, even to a room full of people who know and love frames. So we're going to go back to undergraduate linear algebra and ask, why do we like orthonormal bases? Why are they so interesting? Well, first of all, every single vector in orthonormal basis has unit norm, which we can interpret as meaning each of those vectors are somehow of equal importance. We also have this really nice change of basis formula. So whenever we have a basis, we know we can do an expansion, but when it's an orthonormal basis, we have a very nice formula for what the coefficients of that linear combination are going to be. It's just we take the thing we're trying to represent, and we take inner products with the corresponding basis elements, and voila. Also, the inner products, or the absolute value of the inner products, are equal and optimally small. So what I'm saying is somehow the angles between the vectors are as large as they can possibly be. So one question would be, how can we generalize these traits? And pretty much everyone who's in this room has done some work on generalizing these traits. And there are different interesting research questions in finite versus infinite dimensions. Okay, so we're going to start with finite dimensions and talk about ETFs. So with ETF is a collection. So now instead of being an arbitrary separable Hilbert space, I'm going to think finite dimensional Hilbert space. And because I'm going to be lazy, I'm going to think about just coordinate spaces over the reals or complexes. Then we say the vectors are equal norm if all the norms are equal. We say they're tight if they have up to some universal scaling factor, the exact same change of basis formula. And what's interesting here, as of course, is that this n can be strictly larger than the d. So they don't need to be a basis anymore. And we say that it's equiangular if all the absolute values of the inner products is constant. And when all three are satisfied, this is an equiangular type frame. So equiangular type frames minimize a number of different energy functionals. They can be considered optimal in a lot of different ways. And also they have appeared as sort of emergent structures in neural networks. So I have a ton of hidden slides. I'm not going to talk about neural networks, but some recent work that I've been doing and also work other people are doing have actually shown these things here to be showing up in sort of nature, where the nature is now neural networks. Okay, in infinite dimensions, now we have usually different kinds of questions because the only equiangular type frames in infinite dimensions are orthonormal bases. And so those are sort of understood in some sense. There's still some interesting questions, but for frames, we might ask, we now want our phi to be an orbit or a subsampling of that orbit of some unitary representation. And we want one, i.e. we want the constant norm. I mean, we get that for free with unitary. And two, or some weakening thereof. So maybe not a tight frame, but one of these other things we like to talk about, like Bessel sequence. So put a pin in this. We're going to return to this. But the key thing here is a common question is still involving spinning up a vector with a group. So this is key. So I want you to keep that. For those of you who typically live in the infinite dimensional realm, keep the spinning up a vector as being key in the back of your head as we switch back to finite dimensions. So a lot of known equiangular type frames show a lot of symmetry. So here we have our favorite Mercedes-Benz frame. I've already shown symmetry because you have to rotate it 90 degrees to actually get a Mercedes-Benz logo, but I've rotated it and it's still an equiangular type frame. Some of the Platonic solids give us equiangular type frames in R3. And this is my favorite equiangular type frame of 9 vectors in 3-dimensional space. And we'll say a bit more about that later. So this, you might not be able to see their symmetry, but I'll talk about that later. These, you can kind of think of symmetry in a geometric sense, like Platonic solids have high amounts of symmetry. Okay, so first part of our talk, so half of my title is Paley Fourier ETFs. Okay, so I feel like this is doing some inappropriate things. I'm gonna not let the microphone do that, and I'm gonna reattach up here. There we go. Okay, so I've been playing around with a recent paper and what are known as Paley different set ETFs, and there's some fun number theory and combinatorics that are used to define them, but we're going to look at the smallest non-trivial one here. So we take the all ones vector and we take this diagonal matrix that has certain powers of the primitive seventh root of unity, and we're going to spin up 7 vectors as the orbit of the all ones vector under powers of this matrix, and we get this set of vectors. So we read them off column wise. We have 7 vectors in C3, and this is an equiangular type frame. And it ends up that whenever we have a prime power that's 3 mod 4, we can always construct an ETF that has that prime power number of vectors and approximately half, and the dimension is the number. So we might ask, are there additional symmetries? So just like with the, for example, here with the Mercedes-Benz frame, we can obviously rotate by 120 degrees, but we can also reflect. So we get dihedral symmetry here, even though we can generate this by spinning up by a group of order 3. So here, we're spinning up by a group of order 7, and the question is, are there other symmetries? So first, I'm going to be really explicit in what I mean by symmetries. So we have a collection of n vectors in d-dimensional coordinate space. Then I define a line orthomorphism to be some unitary, so if it's complexes, unitary, and if it's reals, orthogonal, such that if I conjugate the rank 1 projections onto the spans of each of the individual vectors by that u, then it permutes those projections. And that's what I call a line automorphism. And for each line automorphism, they're inducing some sort of permutation of the set 1 to n, just like where is phi j sent to, and that induces that permutation. So we're going to call that subgroup of permutations the line symmetry group. So it ends up that for this set of 7 vectors in 3-dimensional complex space, we have all of these sort of modified modulations are in the symmetry group, but we also get cyclic permutations. And so written as permutations, we can do it in cycle notation, but it ends up being isomorphic to the semi-direct product of Z7 and Z3. And in fact, in general, for the P to the S Paley ETFs, we have this maybe a little bit more complicated characterization of all the symmetry groups. So this was really fun because I was, for the first time since like 20 years ago when I passed my algebra qual, I actually used Gabor theory in a paper. So that was fun. That was fun, actually dusting off some Gabor theory in order to prove things about frames. So ETFs allow you to use tools from algebra and geometry and combinatorics and like draw from a lot of different areas. So if you're not thinking in finite dimensions, if you're an infinite dimensional frame theorist, there's a lot of fun to be had in the finite dimensional realm. Okay, so I'm going to say a bit, how much symmetry is this? So in general, if we just have some group acting on a set, we can say that it is k-transitive if I take any ordered k-tuple with no repeats and any other ordered k-tuple with no repeats, and there is a group element that maps this k-tuple to this k-tuple. And if this is true for every single k-tuple, then it's called k-transitive. Now I can loosen that and say, okay, I'm just going to take any set of k elements, I don't care about the order, and any other set of k elements, and I ask, is there a group element that maps for every set of k to every other set of k? Then I call it k-homogeneous. So k-transitive implies k-homogeneous. And we can think of these as the higher the k is, then the higher the amount of symmetry. So if we have something acting on a set of size n, then intransitive means we have all possible permutations. So we're really getting all the possible symmetries we could get. And so it also ends up that these line symmetry groups of the Paley ETFs are too homogeneous but not too transitive, which there's a lot of interesting like representation theory from the 1970s that I got to like dust off to do these results. So cool. Now we're ready for a segue slide. So because I shoved together two unrelated papers. So here we go. Here's the segue slide. So we're going to fix a primitive third root of unity zeta. And we're going to look again at that collection of the 9 vectors in 3-dimensional complex space. And we're going to write it now as a sort of orbit. It is an orbit of like a projective unitary representation of the vector 1, 0, -1. And we have powers of a matrix that has 1 zeta zeta squared along the diagonal. And then we have powers of the cyclic permutation matrix. And that generates all 9 of these vectors. It ends up that this has 2 transitive line symmetry, which is a pretty special trait. In fact, Dustin and Joey did a lot of work characterizing every single ETF with 2 transitive line symmetry. That also got into representation theory in a way that is above my pay grade. This has a lot of other cool properties, so you might have even seen me talk about other properties this particular set has. And now here's the segue. This is a Gabor equiangular type frame, so because we're spinning something up with modulation and translation. Okay, so now we're here to the second half of my title, Gabor frames over expansible groups. Okay, so we're going to start with G being a locally compact abelian group, so we can think of Euclidean group, integer lattices, finite groups, and forgive me here, I'm going to use this notation of a Blackboard bold capital Z with a subscript letter to mean something completely different in a few slides, but I realized it too close to this talk, so you're just going to have to switch in your head that notation. Here I just mean Z mod NZ, but any finite group, toruses, and the p-adics are another example, and if you don't know p-adics, I'll give you a little taste of what they are later. The main idea is these are abelian groups that are Hausdorff, and their group action and their topology play nicely together. And because they play nicely together, we're able to do Fourier analysis in a sort of natural way. And that is via what's called the Pontryagin dual, G hat. And so these are the group of all the characters from the group. And so we have this long list here. And we just throw some hats on things. So sometimes things are self-dual, like RD. And then other times, like with the torus and the integer lattice, then they are not self-dual. Okay. So we can define translation and modulation. So from L2 of G to L2 of G. For translation, we just act on the input of a function by performing the group action. So here we're subtracting because we're writing our group additively. And then we can pointwise multiply by a character that's been evaluated at the input for modulation. So going back to my favorite set of 9 vectors in 3-dimensional space, we have that our group is Z3. M sub k, the modulations are just exponents, powers of this diagonal matrix here, and T sub L, these are just exponents, powers of this cyclic translation matrix. So we can also say, what is a Gabor system? So we fix a phi in L2 of G and some subset lambda of G cross the G hat. And we define S of phi comma lambda as just all of these modulation translations of phi where the modulation translation set is determined by lambda. So tying it back to the first half of the talk, no matter what G is, we always have that the product of G and G hat is always in the line symmetry group of S of phi comma G cross G hat. So those 9 vectors in 3 dimensions definitely had a symmetry group of at least 9 because all the translations and all the modulations are going to spin up the vectors. And it ends up that one has more, but there are other Gabor ETFs, finite Gabor ETFs that don't have additional symmetries. They just have the translations and the modulations. Okay, so what are some important open problems involving Gabor? So there's Zauner's conjecture. So this is actually the strong version of Zauner's conjecture, but it says that for every D, there exists a phi in CD. So CD here is little L2 of ZD. where the Gabor system generated by all the translations and all the modulations is an ETF. So this is an open problem. There's currently not even an infinite class of known D where this works. But I will say right now, the current direction of potential proof seems to be something that involves algebraic number theory that is also way above my pay grade. That doesn't mean that's the way it's going to be solved, but that at least is the direction that research is going right now. Then there's the HRT conjecture, which says that for any phi that's non-zero in L2 of RD and any lambda that is finite, the Gabor system generated is linearly independent. Then we have, for fixed phi in L2 of RD, find all lambda for which S of phi comma lambda is a frame. So I believe Ola's here somewhere in the, there we go. He had listed this as one of the 7 cross out, now 6 big problems in frame theory that are left. And then what I'm going to be talking about is now we're going to look at more general locally compact abelian groups. So what are necessary properties for lambda such that we can have a Gabor system over lambda that's approximately a frame from L2 of RG. So by this, I mean, you know, maybe Bessel sequence or respaces or these things that are all the sort of frame adjacent questions. All right. Okay, so one thing that Chris is very, very good at is writing these very, very long, detailed, thorough, complete, whatever other synonyms you want to throw in, review articles that are very, very useful. So this review article was on density theorems in Gabor frames, and I read it as a little grad student preparing for my oral preliminary exam. When it was still just a free document that he just had on his website that he had just written for funsies. It's now published, but at the time it was just, here's, 50 pages of blood, sweat, and tears just for y'all to enjoy. And I did read it very, very intensely. So I'm going to boot to the now published version in JFAA for all the references that you might want to do, because there's no way that I could list everything that came into these results without this bar kind of creeping up here. Okay, so we're trying to think about what are necessary conditions for us to have a Gabor system that has certain frame-like properties. And we're looking here in the case where our locally compact abelian group is just is Euclidean group, it's RD. And so we're going to define a subset of lambda, or lambda to be a subset of RD, and Q sub Rx to be the cube with side length R that's centered at X. Then we have 2 very parallel definitions. So I'm going to define this one on the left here. So I'm going to take a cube, and I'm going to fix an X and an R, and I'm going to intersect that cube with my lambda, and I'm going to count the number of points at that intersection. And then I'm going to divide by the volume of the cube, which is determined by the side length. And then I'm going to, for a fixed side length, take the sup over all the possible shiftings of this cube and counting the number of points of lambda that land in it. And then I'm going to take the lim sup over all the possible side lengths. And that is defined as the upper Berling density. And now I'm just going to take the 2 mentions of sup and replace with inf, and that's going to be the lower Berling density. And these play a really powerful role in trying to determine whether or not a Gabor system could even possibly be a certain frame-like system. So I'll note here that the integer lattice has upper and lower Berling density equal, and both are equal to 1. And in general, if you have a lattice, the reciprocal of the volume of the lattice is going to be the upper and lower Berling density. So in a sense, one can view the Berling density as saying, how far off are you from really being a lattice, right? So you're perturbing a lattice in a sense. And the framiness properties of the Gabor system has to do with certain boundedness of these different densities. So if you expect your Gabor system to be a so-called Riesz sequence, then you get this alpha is 0, and we get a 1 here, and there's a long list of these things. See this review paper if you want all the, I think, 7 different parts of the ways you can fill in these alphas and betas. Okay, so now I'm going to make a little detour. Personal side note. I'm not sure how many of you were here in FFT in 2009. So this was the first year after Yanni had left. And so we no longer had the pony keg of the Norbert Wiener Red Lager. So it's Thursday night. Yeah. So I don't know if it's Wojtek or Kaso or John or Radu, but someone thought that they should buy a full-sized keg for the Thursday night reception at FFT 2009. And Chris Shaw, who is what was his official title? Associate Director of the Norbert Wiener Center, was just walking around, and you wouldn't even be looking. He was filling your cup with more beer. So it was a rough morning that next morning when I was sitting there at the first talk. I felt like death, and there was a really important mathematician who was giving a talk. And then they said a statement that I was able to correct because of Chris Heil. It was the proudest moment of my grad school days. So from that exact review article, we have this line that we have an example of a Gabor system that is complete. So think of spanning, hand wavy, if you don't know what that means, where both the upper and lower Berling density is 0, but it's not a system of pure translations. And the speaker had said it is unknown if such a system exists. And I, barely able to move my body, raised my hand, slouching back in my chair, and I was able to say, no, it is known. So thank you, Chris, for giving me the proudest moment of my graduate school career. So anyways, if you're not reading what Chris Heil is writing, then you're really missing out. So these are great review articles. Okay, so let's get back to it. Even though Berling density is about sets that don't necessarily have algebraic structure, it's still somehow trying to compare it to sets with algebraic. Like algebraic structure, like a lattice structure, is underlying a lot of things that we do, not just in Gabor, but in general in harmonic analysis. So Guido Weiss said at the SPIE Optics and Photonics in 2013 that the group that's really important for real wavelets is the integers. And Carlos and Vicky said in their paper Shift Invariant Spaces on LCA Groups in 2010 that also when it comes to the theory of shift invariant spaces, the really important thing here is the action of this subgroup ZD. So lattices are key to a lot of what we do. And in fact, the very first frame theory paper, the one that we all know and love, Duffin and Schaefer, 1952, I mean, the purpose of this paper and the inspiration was saying, let's take the orthonormal basis that we get of L2 of the torus, and then we're now going to perturb off the integer parameters, and we want these parameters now to be close to Z, and when they're close to Z in some sense, we get this new thing called a frame. So even the entire founding of our field was, let's perturb a lattice, but you still are thinking about that lattice. Also, the Gabor density theorem over lattices is much more descriptive, and over rectangular lattices even more so. There's a lot more you can say. MRA and wavelet theory relies on translating by a lattice. So here I'll plug another review article. This is of Chris and Dave, and this is I think your very first publication according to MathSciNet. It has about a third as many citations as Duffin and Schaefer, but it's doing pretty well. It's doing pretty well. But not all locally compact groups have a lattice. So by lattice, I am defining this to be a discrete co-compact subgroup. Okay, so what are we going to do? First, I'm going to give you an example of a locally compact abelian group that has no lattice. So we're going to fix a prime P, and we are going to find the p-adic numbers as meromorphic expansions in P with carrying. Okay, what do I mean here? So meromorphic expansion means I have some coefficients and I have some powers of P, and the powers of P can have a finite number of negative exponents and possibly infinitely number positive exponents. And then I'm going to choose these coefficients to be between 0 and P minus 1. So this choice of coefficients between 0 and P minus 1 might make you think we should be adding mod P, but we're not. This is what the carrying means. So if we have one expansion, that is P minus 1 times P to the first, and another expansion, that's 1 times P to the first, then those add up to be P squared, just like normal arithmetic. That's not 0P. So we're really kind of treating these like numbers, and we're carrying across the different powers of P. And the p-adic integers are now power series expansions in P with carrying. And so now we no longer allow there to be any negative exponents. And it ends up that the p-adic numbers have absolutely no lattice. Also, very confusingly, these p-adic integers are a compact open. They're a unit ball with respect to this thing called a p-adic valuation. Even more confusingly, these are the completion of the normal set of integers with respect to this p-adic valuation, but you get something compact. That's weird. Also, multiplying by P shrinks sets. So we actually have a Haar measure here, and so it's not just that P times ZP is a strict subset of ZP, it's that the Haar measure is also strictly smaller. Oh, and here's that different use of subscript letter that I promised was coming. So this does not mean Z mod PZ. It literally means these expansions here. Okay, so people who work in p-adics like making pictures like this that are showing the weird topology. I'm not going to get too much into the topology, but the p-adics satisfy what are called the strong triangle inequality, which means you don't have any non-trivial intersections. There's a lot of quirky but fun things when you're dealing with the p-adics. Okay, so the question is we want to try to define a density theorem for Gabor systems over locally compact abelian groups like the p-adics. Some people have published some results in this direction, but they often have still required that the group has a lattice. So here, we're not assuming this at all, because the kind of one of the most canonical examples of a locally compact abelian group does not have a lattice. So what we're going to do is we're going to take G, a locally compact abelian group with Haar measure mu, H, a subgroup that's compact and open. So with the p-adics, for example, we're going to choose the p-adic integers. And then we're going to fix A to be an automorphism of G. And the reason that John's name appears here with his, I like to say, blood son rather than a math son like Chris is a blood son who does math rather than a math son. There's a distinction. So they did a work on wavelets over local fields, which would include the p-adics. And just as I mentioned before, even doing multi-resolution analysis, you need a lattice, and you don't have a lattice. So they came up with a way of making translations that weren't really translations, but acted like a group, and basically as close as you could get to translations that acted like a group, and then define their wavelet theory based on that. So we took those ideas and used that in order to define a Berling density. So we say that A, this automorphism of our locally compacted group G, is expansive if multiplying our compact open group by it expands it out. And also, if we take the intersection of all the negative powers of this automorphism of H, then we get precisely 0, the identity in our group. Okay, so if such an A exists, it's an expansive group. And we define very similarly upper and lower Berling density. So now the main difference here is that instead of having our cube, we now are taking powers of A applied to H, and you're sifting it by X. And this volume has been replaced by taking the ratio of the Haar measure of AH with the Haar measure of H. And this is independent of the automorphism. So that's an important thing to note because it's defined using the automorphism, but it's independent of that. And to finish up, the key idea is we get all of the same results except for the completeness results. We didn't do that. We even get something, we define a modulation theory, and if we have phi being in a modulation space of G and the upper Berling density is finite, then we actually get its Bessel. Some of the proofs are nearly identical to what Chris and other co-authors had done, and some required new techniques, especially the ones where the original proofs required complex analysis, which we didn't have at hand. So group structure is great. Here's Chris in his happy place celebrating Carlos's birthday, and happy birthday.